Hello everyone, and welcome back to the channel. Today, we're journeying back to the tail end of the 20th century, a time of immense optimism and ambition in space exploration. The internet was booming, the world was on the cusp of a new millennium, and NASA was operating under a bold new mantra: faster, better, cheaper. This philosophy was designed to usher in a new era of rapid, cost-effective interplanetary science, sending more probes to more places than ever before. At the heart of this initiative was the Mars Surveyor 98 program, an ambitious two-part mission to unlock the secrets of the Red Planet. And its flagship, the vanguard of this new approach, was a sophisticated spacecraft called the Mars Climate Orbiter. Launched on December 11, 1998, this wasn't just another satellite. It was a $125 million weather station for an alien world, designed to study the Martian atmosphere, its climate, and the seasonal changes that sweep across its rusty plains. For 286 long days, the orbiter performed flawlessly. It soared through the cosmic void, covering a staggering 416 million miles. On the ground, teams of brilliant engineers and navigators at NASA's Jet Propulsion Laboratory, or JPL, meticulously tracked its progress. They sent commands for tiny course corrections, known as trajectory correction maneuvers, nudging the probe with unimaginable precision. Imagine trying to throw a dart from New York City and have it land perfectly in the center of a specific keyhole on the Eiffel Tower in Paris. That's the level of accuracy we're talking about. The entire mission was a testament to human ingenuity. As September 23, 1999 dawned, anticipation in mission control was electric. This was the day. After its 9-month voyage, the Mars Climate Orbiter was about to perform its most critical maneuver, the Mars Orbit Insertion Burn. It would fire its main engine for 16 minutes to slow itself down just enough to be captured by Mars's gravity, settling into a stable, elongated orbit. From there, it would act as both a climate scientist and a vital communications relay for its sister mission, the Mars Polar Lander, due to arrive a few months later. The final commands were sent. The probe turned to the correct orientation, ready for its big moment. At 2 a.m. Pacific Daylight Time, the spacecraft slipped behind Mars as planned, cutting off its radio signal from Earth. This was expected. The team waited, clocks ticking, for the orbiter to re-emerge on the other side, its engine burn complete, safely in orbit. But the minutes stretched into an agonizing silence. The expected time of reacquisition came and went. Nothing. Just the faint, empty hiss of deep space. The $125 million probe, the culmination of years of work by hundreds of people, had vanished without a trace. What could have possibly gone wrong? Initial theories flew around mission control. Did a critical component fail? Was it a software glitch? Did a solar flare knock it out? The truth, when it was finally uncovered, was far more mundane, more unbelievable, and infinitely more embarrassing. There was no catastrophic explosion or alien interference. The Mars Climate Orbiter was lost because of a mistake so simple it's taught in middle school science classes. One team of engineers used the imperial system of measurement, while the other used the metric system. It was a failure to do basic unit conversion. A simple mix-up between pounds and newtons, between inches and meters, sent a state-of-the-art spacecraft to a fiery, multi-million-dollar death in the Martian atmosphere. Today, we're going to unravel exactly how this colossal blunder happened, follow the chain of missed opportunities that allowed the error to go unnoticed, and explore the critical lessons NASA learned from this incredibly expensive and very public failure. To understand how a spacecraft can be lost to a simple math error, we need to look at the division of labor on the mission. The Mars Climate Orbiter was a collaborative project, but the two key groups in our story were separated by over 1,000 miles. In Denver, Colorado, you have the engineers at Lockheed Martin Astronautics. They built the orbiter and, crucially, developed the ground-based software that controlled it. Meanwhile, in Pasadena, California, you had the navigation team at NASA's own Jet Propulsion Laboratory. Their job was to pilot the spacecraft, to plot its course and ensure it arrived at Mars at the exact right place at the exact right time. The fatal error occurred at the intersection of these two teams in a piece of software called the Angular Momentum Desaturation, or AMD file. It sounds complex, but its purpose was relatively straightforward. As the orbiter flew through space, its reaction wheels would spin to keep it stable, but they would gradually accumulate momentum from forces like solar wind pressure. To manage this, the spacecraft would periodically fire its small thrusters in tiny, controlled bursts to desaturate or offload that momentum. The Lockheed Martin software on the ground was responsible for calculating the force or impulse of these tiny thruster firings. The software did its job perfectly. It calculated the impulse and generated a data file. That file was then sent electronically from Denver to Pasadena. Here's where the disaster was set in motion. The software specification document, the contract that defined how these two systems should talk to each other, required that this force value be expressed in the metric unit of Newton seconds. It's the standard for virtually all modern scientific and engineering work. However, the Lockheed team programmed their software to output the value in the old imperial unit, pound force seconds. For anyone who's not a physicist, 1 pound of force is equivalent to about 4.4 newtons. So, the numbers being sent from Denver weren't just a little bit off, they were wrong by a factor of 4.45. Every single time the thrusters fired and the software in Denver calculated the effect, it passed a number to the JPL team in Pasadena that was nearly 4.5 times smaller than the actual force exerted on the spacecraft. You might be asking, how could nobody notice this for 9 months? The answer is a chilling lesson in human factors and confirmation bias. The navigation team at JPL see anomalies. After each trajectory correction maneuver, they would measure the spacecraft's actual position and compare it to their predictions. And they noticed that the orbiter was consistently slightly off course. There were small but persistent navigation errors. However, instead of suspecting a fundamental flaw in the data they were being given, they attributed these discrepancies to more typical expected variables. They assumed the tiny errors were due to the spacecraft venting gas in a way they hadn't perfectly modeled, or that the physical properties of the thrusters were slightly different from the spec sheet. They had a set of plausible explanations, and the data seemed to fit, so they adjusted their models to account for the noise without ever questioning the integrity of the core numbers they were receiving. It's a classic case of seeing what you expect to see. The error was hiding in plain sight, masquerading as routine operational variance. This continued for the entire 286-day cruise. With each thruster firing, the real-world trajectory of the orbiter deviated further and further from the one that existed in JPL's computers. The team in Pasadena thought they were guiding the probe towards a safe orbital altitude of about 150 kilometers above the Martian surface. But, in reality, the cumulative error from the unit mismatch was steering it on a collision course. The fatal final trajectory sent the probe skimming through the upper Martian atmosphere at an altitude of just 57 kilometers, far below the 85-kilometer limit where a spacecraft of its design could survive. It entered the atmosphere at immense speed, where it would have experienced intense friction and aerodynamic stress, causing it to break apart and burn up into a multi-million-dollar meteor shower over Mars. The loss of the Mars Climate Orbiter sent a shockwave through NASA and the entire aerospace community. It wasn't just the loss of $125 million, it was a profound and very public embarrassment. The cause of the failure was so elementary that it was almost comical, and it called into question the competence of an agency revered for its precision. Immediately, NASA convened the Mars Climate Orbiter Mishap Investigation Board, a team of internal and external experts tasked with figuring out what went wrong. Their final report, released just a few weeks later, was a scathing indictment not of any single individual, but of the entire system. The board concluded that the root cause was the failure to use metric units as specified in the contract, but they dug much deeper, exposing a cascade of systemic failures that made such an error possible. It was a perfect storm of broken processes, poor communication, and inadequate oversight, all exacerbated by the relentless pressure of the faster, better, cheaper philosophy. The investigation revealed several critical breakdowns. First, there was a total failure in verification and validation. The software that outputted the data in pound-force seconds was never properly tested by the team that would be using it. There was no end-to-end simulation where the two systems, Lockheed's and JPL's, were run together to see if they communicated correctly. This simple test would have immediately flagged the discrepancy. Second, communication between the teams was flawed. The navigation team in California had noticed the trajectory anomalies but failed to formally report them in a way that would trigger a deeper investigation by the engineers in Colorado. The two teams were operating in their own silos, not as one integrated unit. And third, the project was simply under-resourced. The investigation board found that staffing for mission-critical operations was insufficient, and the training for new team members was inadequate. In the rush to do things cheaper, corners were cut on the very processes designed to prevent these kinds of mistakes. The scientific loss was immense. The orbiter was meant to be the first interplanetary weather satellite, providing daily maps of the Martian atmosphere and helping us understand its climate evolution, a key question in the search for past life. Its loss also doomed its sister mission. The orbiter was designed to be the primary communications relay for the Mars Polar Lander, which arrived at Mars in December 1999. When the lander went silent during its descent, the lack of a relay in orbit made it incredibly difficult for engineers to diagnose what had happened. The failure of both Surveyor 98 missions was a devastating 1-2 punch for NASA's Mars program. But from these ashes rose a renewed commitment to rigor. The faster, better, cheaper mantra was abandoned, replaced by a culture that prioritized mission success above all else. NASA implemented sweeping reforms, mandating strict adherence to the metric system, enforcing rigorous end-to-end testing for all software and hardware interfaces, and improving communication protocols between its centers and contractors. This painful lesson directly contributed to the spectacular success of the missions that followed. The Mars exploration rovers, Spirit and Opportunity, and the Curiosity and Perseverance rovers all benefited from the hard-won wisdom of the climate orbiter's failure. It stands as one of history's most powerful reminders that in the unforgiving environment of space, there is no such thing as a small detail. The fate of a mission can hinge on something as simple as checking your units. What do you think is the most shocking part of this story? The simplicity of the unit era itself, or the fact that it went completely unnoticed by brilliant engineers for 9 months? Subscribe to learn more, and see you soon.